We have here with us Professor Hjort from Uppsala University. He will keep talking about microfluidics, in this case, under high pressure conditions, and the screen is yours, Professor Hjort.
So, this should be in presentation mode, I hope, and I should be sharing.
Excellent. Now it is okay.
So, thank you for inviting me, and it's a pleasure to be here and talk about high pressure microfluidics and chemistry. Just like Manuel said, this is nothing you do with PDMS. You need a stiffer and stronger material, very often using silicon, and you're using the mature technologies that have been developed. You have to remember, in miniaturized and microsystem technologies, all the sensors and actuators, well, at least more than 90% today are made in silicon, although most of us in science and engineering at the universities work with other materials. So my background is a material scientist. What I know especially is the mechanics and the manufacturing of the small systems. With Emmanuel's great introduction to how you manufacture and how you can use the silicon technology, I think I can go much faster here. And I will focus on high pressure microfluidics. And you can see here good reasons why you should use high pressure microfluidics, but I would actually like to bring up specific things. That is, you can get much higher precision by using higher pressures. It's easier for you to get higher solubility, higher isothermal control, higher density of fluids. Many things become so much easier if you work with high pressure. However, there are some issues. A major thing is the fluidic capacitance. If you have a rather large system, you know we talk very much about lab on a chip. Frankly speaking, it's usually a chip in the lab. And all the external equipment in a fluidic system will change the time constant by the capacity, the microfluidic capacity. So the capacitance may be that if you work with very high pressures, the system will be rather slow. This is quite much what we've been focused on, and you will see how to create better control and more precise microfluidic or capillary fluidic systems by using microfluidics. In chemistry, of course, extraction, synthesis, and analysis excel at high densities and high temperatures. If we look to bioextractions, it's a huge endeavor to do experiments to find the extraction parameters. With miniaturized devices, you can do it immensely much faster. If you look microreactors, those are excellent when small quantities are sought for drug synthesis, for personalized medicine, or when working with short-lived radioactive biomarkers, whether it's for molecular imaging or radioactive immunoassays. But obviously, the main area and where the capillary physics are very much seen is in the analytical chemistry and bioanalytical chemistry. It gives low time constant, small sample volumes, and low consumption that really is of advantage. Already in the 90s, we find commercial devices in microscales by using LIGA technology like these from IMM and the pilot reactor for BASF. And in the early 2000s, we saw the first commercial HPLC chip from Agilent that could be directly connected to mass spectroscopy to allow these orthogonal systems that are very good to use. Challenges when we're working with these, if we look into an old Nestor like Klas Hjort in MIT, is very much the materials. Hard materials like we often use, like glass, stainless steel, or silicon, have problem with particles, which may block the actions of pumps and valves. And there are several missing components in the miniaturized scales: seals, valves, micropumps, handling of solids, back pressure regulators. I liked Emmanuel's use of Viton gaskets. It's rarely done, but Viton is a very nice material for certain chemical systems, and it could use much more. And it's easy to replicate and machine in high resolution. Long ago, like 15-20 years ago, we started working on stainless steel systems, which is very often used for reactors in chemical systems, as you know. And this is an example of a 6-lever laminated metallic micropump. It allows ultra-low pumping without any back pressure or back leakage, as the whole system is with active valves, and we're using paraffin that is extremely strong. With that, you can go sub-microliter per minute pumping, and you can go above 200 bar in pressure resistance. This is, to our understanding, the still for nearly 2 decades, the strongest mechanical micropump that is in this size. Of course, dynamic pumps like electroosmotic or dynamic electric pumps can be much stronger, but you have to remember, just like between HPLC and electrochromatographic systems, you often get a superior stability if you use mechanical pressure rather than electrical pressure, due to the set coefficient of the material and how that changes. Here are examples also of micromachine valves and gaskets that can be done. Actually, one in the middles there are actually in Viton. Was made, well, 15 years ago, something like that. That is not what I will focus on. I will actually focus on what Emmanuel was talking about. Lithographically and micromachine devices in silicon and glass. And when we did the stainless steel stuff, we always worked with clamped systems to reach high pressure capacity. With the strong bonding and the miniaturized devices that you have in silicon or glass microfluidics, you do not need to have a clamped system. Also, if you go up to 700 bars or so, it's all a question about the sizes and the thickness of the material. And we often work above the 100 bars and around the 200 bars for our systems. And I will especially focus on a very nice and simplistic use, and that is thermally controlled high pressure microfluidics, which this PhD student Simon Söderberg and Carolina Svensson have now been working with for 5 years, just about making their dissertations. And what we do is using the change of the dynamic viscosity of the material. So you can see here how the viscosity is changing with, for example, methanol or water, and that then is directly coupled to the change in pressure. So you create a restrictor and you get a valve that is possible to use as a regulator. Emmanuel talked about integrated resistive heatings. Here we have put the resistive heaters next to the meander. So it's just a couple of microns away, and you get a very rapid control of the temperature, and by having the right geometries, you can also get a good stability. The first structure you see there, then the heating is exactly the same all over the meander, but then when you're flushing the microfluidic through the meander, not with very high speed, something like a few microliters per minute, the thermal load and the heat capacity of the liquid will transfer the temperature downwards in the fluid. So first things first, one thing that was missing is back pressure regulators. So what we are using this meander structure now behind the actual applications, for example, a chromatograph system. The principle is, if you change the pump flow rate, you will have a change in the pressure upstreams. You see downstreams, and so this is not actual a presentation of the back pressure regulator. This is to show a principle. Now, if we start to change the power of the heating, we can create a very stable pressure instead. However, we have the problem with compressibility. So here you can see that if we don't do anything but just letting the pressure be there and making a change, how very long, and we're talking about many minutes before you get to stable system if you just use a first order of the system and no control. This goes directly with the upstream volume. So how much capacitance, otherwise incompressible fluids like water has when you go up to 100 bar. And here you see that with a pump volume of 100 milliliters, the time constant is in the order of several minutes in increasing pressure. Much shorter in decreasing pressure, because there you're heating up the system, in the other you passively cool down the system. That we solve by using ordinary PID control. With that you can improve very much the performance and reduce the time spans. So just not working with a constant temperature, constant power, but moving much higher power for a short period and then calibrating this in by control systems. So for back pressure regulator, we can show with a dead volume at 3 nanoliters. And the smallest dead volumes for commercial back pressure regulators are in the several microliters, and normally they are up to milliliters in size. But at 3 nanoliters, we have the same control in pressure tolerances as commercially available options, and much faster reaction. Now, you don't need to use it as a back pressure regulator, since it is such a small dead volume. You can put it in front instead and use it as a pressure and flow regulator. Just the same thing, but above the system that you want to use. And doing that, instead of having 3 pumps in a microchip system, this is a collaboration with Professor Bellner at the University of Leipzig, we could very much reduce the complexity of the chip HPLC system and also increase the performance as we get a much lower microfluidic capacitance in the upper layers. And you can see the regulator power, how stable the pressure is when regulated, compared to how the pump cycle changed in the systems. This is an ordinary HPLC pump. You can also use this for mixing the right solvents. Here is an interesting fact, if you don't know that. At this modular system where there are 2 regulators, 1 mixer, and a dielectric or permittivity sensor. The solubility is very strongly related to the dielectric constant. So we can, by measuring the dielectric constant of the mixture, very precisely decide that we have the right solubility for the mixture. It's a very simplistic way to measure. And it's physical, which makes life easier than if you want to measure electrochemically. So continue with the pressure and flow stabilizers. We are heating now above the system. we are looking into stabilizing different pumps. So before we regulated, but now we use the buffer capacity to use first the damping effect that you have a restriction. So if you look to an HPLC pump, a Harvard pump, or an ISCO pump, without the chip, you have a certain variability of the pumping stroke downstreams. Just putting a passive chip will very much reduce the variability because you're damping the system. But that is just locally. Then actively, you can control variations. And then depending on how high the pressure is, because unfortunately we are using a control system here, an external pressure sensor as a control measurement, and the precision of that system, that pressure sensor, was just about 0.03 bar, which makes the best quality in control for these systems. But if we work with high pressure ISCO bar systems, of course we get a much lower relative change from the sensor. So you see here how large a Harvard pump varies without a restrictor. As soon as we put in a restrictor, it goes very well. But here you don't see a change. Here you don't see a change in when you put in the active chip, because the variation is too small for the pressure sensor to make. All the other, the HPLC pump and the ISCO pump, you see how much more stable the system becomes when you have an active control. Finally, we're using this also to create stable portable HPLC pumps, because here you can have a very small high pressure source to pressurize the system. I mean, just by high pressure gas. But with a small system, you will all the time change the output pressure from that source, and you need a pressure stabilization below. So using small high pressure vessels to drive the flow demands a stabilizing chip, but it's possible to get then high volume, high pressure flows without any high power electrical pumps and compressor. And all of a sudden you can take all these high pressure analytical tools on the field without high weights. This is battery driven at 9 volts. At this example, you see a 32 bar system. You see the first top, how it is measured with ordinary HPLC, and below when it's driven, gas driven. And frankly speaking, you don't see a difference. Conclusions on stabilizers. You can get relative precisions down to the hundreds of ppm. Accuracies that are even better against external pressures. In here we are in a little larger dead volumes, but it's 60 nanoliters. And that can be integrated in a micro total analysis system. Finally,
Professor Hjort, I think we are out of time.
Yeah, so I will take this final just, and then sorry. Finally, we can do this in silicon as well, and with silicon you can put high pressure pressure sensors inside the fluid channel. That gives you an in-line pressure, flow, and temperature set in 25 nanoliters. You can work up to 200 bars with the system, and if you have heaters to that, you can also use that as a regulator. And with that, thank you so much.
Thank you very much, Klas. Amazing capacities also from your side. So it's already half past, but maybe if the panelists, if the panel members don't mind, and also Miriam, we can extend the meeting for 5 more minutes if someone wants to ask something for discussion. Also, the panel members can actually ask the others if they want.
Well, if I start, I mean, I
Yes.
totally believe in silicon-based microfluidics, but when we use it, usually it is with integrated electronics for creating better high-resolution IceFETs or to make nanopore systems for DNA and proteomic studies. Emmanuel, you were talking about CMOS systems, and I think that is really key if we want to make more complex systems. To combine high pressure capacity with the silicon glass systems, but also using integrated electronics. Could you talk a little about what IBM is doing there?
I mean, not really.
Okay, then you don't.
I mean, talking about compatibilities mainly material-wise and just from the platform, having now sensors operating at these high pressures requires a lot of changes in compared to the traditional sensors that we have. I mean, I've given examples how you can interface with the channels, with the electrodes and the optics. So I can also imagine having existing components that will be integrated on another chip. And if you do a rational, clever design, you can probably take the signals from the channels. So it's going to be like two silicon devices that you kind of stack together.
But it's rather system in package than
it's rather packaging approach. Yeah, it's rather packaging approach. I mean, we worked here in Zurich a lot on chip cooling using direct water cooling at the bottom of the transistor carrying level. And I mean, that comes along with a lot of issues we haven't foreseen, like the bonding structures that need to be corrosive resistance against the coolant, and having 3D and liquid carrying channels. So it definitely has a certain complexity that you need to engineer. But I think for simpler devices, having a stack and then engineering it and stacking it together can definitely be feasible. So
we also learned about the problem with stress-induced corrosion when you work with silicon glass systems, and all of a sudden when you are above a certain threshold, nothing can hold with time, especially if you go to high temperature systems. Yeah,
it's the stress engineering is a major point. I mean, even in electronics, but then also the different CTEs that you have when you operate at different temperature. You have locally different temperatures than the CMOS part. I think this is not straightforward at all. So I hope that I haven't provided a wrong impression, but it may be feasible just from the material point of view, but engineering wise, it's a lot of things that need to be taken into considerations.
But I totally agree. But is there any questions or comments from the audience?
I have one question for you, Klas. But first, there was a question to Professor Wilhelm Hack. Actually, well, maybe I can give the word to him. There was this question by Michael Mayer about the logistics of using chemical reaction networks to do classification. If you want to use the system to classify the pictures of cats and dogs, how would you relate the input image to the chemical inputs of your reaction system, concentrations, pH, temperature, etc.? So
I can answer that. So that's possible. It's not very practical because it would take a long time. So I think you wouldn't do that necessarily. But the way you could do it is, for example, that you say, for example, you take a certain picture, has lots of different pixels, and say the pixels can be black and white. So what you would do is you would say, I'm going from the top to the bottom and then up again and down, up and down, column after column after column. And every time when your pixel is black, you say that's a 1, and you say formaldehyde input would go up. And then if it goes to a white pixel, it would go down, and the formaldehyde concentration goes down again. And you work through all your pixels. And then what you could do is, instead of going top and bottom, you would say, I'm going left and right, left and right, left and right. And that would be my second input, for example, dihydroxyacetone. And you would do the same thing. You would say, okay, if it's black, it goes up. If it is white, it goes down, etc., etc. So you essentially digitize the sort of information from the pixels that you have in your picture into change in input conditions of your chemical reservoir. So that's also why you would say that's a bit slow, right? Because it means that pixel after pixel have to sort of work through a change in input conditions, which would then take a certain amount of time to reach a steady state, and then you measure it. So that's why we definitely need at some point the reactors that Emmanuel was showing, because you can only do this in a fast way if your reactor volume is very, very small. So in our case, it would take too long. But that is roughly how you would do it.
Thank you, Wilhelm. Klas, I have one question, and maybe Emmanuel and Wilhelm can then intervene if they consider it. So one of the important things in the project is actually the inline analytics that comes out of the reactor, of the composition of the CRNs. So I liked a lot the last part of your talk, and I was just wondering what type of detection methods could you couple to these high pressure HPLC columns, portable HPLC columns and so on? Could you couple that to a mass spectrometer, other spectroscopy techniques?
I mean, there is no difference from any other HPLC system. So, as you probably know, the most sensitive systems today are actually electrochemical cells, if it is the right chemistry. And you can, from Thermo Scientific, buy these microfluidic systems to put at the very end. If you want to go orthogonal, I mean, there are good reasons to have two HPLC systems orthogonally when you know where to go, and also to use mass spec. That is standard procedure today. I worked rather much on how to get different kind of electrospray ionization nozzles from the microfluidics, but that is like 2 decades ago. But there are good ways to do it today with high quality.
Thank you.
But to build a mass spec, a miniaturized mass spec, that is still something a lot of people work with and dream about. We're back to this thing. I mean, when the BioCore instrument was created in 91, the first microfluidic system for life sciences with several tens of valves already then. They had the company, Pharmacia Fine Chemicals here in Uppsala, had been working for a decade because they thought they would make something like a pen-sized, all-inclusive chemical analyzer. But of course, thermal stabilization needed a much larger equipment. So what we see nearly always are that if you want to have stable results, the microfluidic chip will just be a part in a large instrument. But with that, we have all the this generation of genome sequencing machines. Everything is microfluidics, but it is in a very large system.
Thank you.
So I'm sorry, but I have to leave in like 2 minutes.
Yeah, I will close the meeting. We are clearly over time. So
yeah, but I appreciate that, and it was really nice meeting the other groups. And although Wilhelm, I do not understand the complexity of your chemistry, it was fabulastic. And Emmanuel, I understand much more your type, and therefore I'm really curious to talk more about this later on.
Yeah,
Wilhelm, I have to read more about yours, and I'm sure we could find combinatorial interest here as well.
Sure.
There you hear my alarm. That means the bell is off, and I have to say hi.
Okay.
All the best.
we appreciate your assistance. And I would like to close the meeting, of course, for thanking all the people attending, and also thanking Miriam Frances from Accelerman, who was responsible for organizing this. So of course she deserves our gratitude. And yeah, I don't know if no one wants to say anything else. Yeah, I say goodbye and hope we meet soon.
Thank you, Andres, for inviting us. Bye.
Bye.